Jason, we miss you. Time to come back. Okay, so today we are going to use tangent lines in a really powerful way to compute limits. And the technique that we are going to talk about, which is called LHopital's rule, was developed early on in calculus. William LHopital did not actually create this rule, but he published it in the first calculus textbook ever, 1696. And it became famous with his name. And it was presented as one use for the derivative. So I want to consider a situation in which the functions f and g both go to 0. And I want to consider the limit of their quotient f over g. Okay? Now you guys have enough experience to know that when you're confronted with a limit, the first thing you're going to do is, and what's the form in this case? It is the indeterminate form 0 over 0. Now I've promised to you that in such circumstances we can find a common factor and cancel and blah, blah, blah. That's all fine. What L'Hopital does is he said, well, if in fact f and g both go to 0, then the limit of their quotient f over g, as it turns out, is equal to the limit of the quotient of their derivatives, f prime over g prime. Now this is a remarkable result, and I'm going to give a proof in a special case for you, in which it will be revealed that the common factor that we're talking about is simply x minus c. So, I'm going to give a partial proof for a special case where f prime and g prime are continuous at x equals c. Now, since f prime and g prime are continuous, that means they exist, and therefore f and g are both continuous also. And so that means if f prime and g prime are continuous at x equals c, then that means that our condition that the limit of f and the limit of g are equal to 0 really comes down to f of c equals 0 and g of c is equal to 0. So this condition that we're talking about right here implies that f and g are both continuous at c, which means that the values of the functions equal the value of the limit, which is 0. Now, since that is the case, and since f prime and g prime are continuous at c, so that f prime of c exists and g prime of c exists, therefore, I can estimate f and g for x close to c with their tangent lines. So if I consider the quantity limit as x goes to c of f of x over g of x, the limit as x goes to c is most certainly considering x's that are close to c. And therefore, I can replace f with its tangent line, f of c plus f prime of c times x minus c. And I can replace g with its tangent line, g of c plus g prime of c times x minus c. And what justifies this is that we're talking about x is close to c because that's what a limit is. But now, what is the value of f of c?
0.
And what's the value of g of c?
0.
Also 0. So I can substitute in 0 for both of these, and they disappear. Look at what's left. F prime of c over g prime of c times x minus c.
There's my common factor.
Of x minus c. It was hidden in the tangent lines. So that what I get is f prime of c over g prime of c. But since f and g are both continuous, that's exactly the same as the limit as x goes to c of f prime of x over g prime of x. Now, this is a proof for a special case here. When you take Calc 2, we do the proof for the entire theorem. No special cases involved. But that proof is too complicated for us, so I'm just going to ask you to take it on a little bit of faith that this result works out in all cases. Does that make sense to everybody? Okay. So we see why it's true, and why it's true that the important thing to recognize in the questions that came up in the other class is how you get from here to here. We get from here to here by recognizing that f of c and g of c are both 0. And that condition was the if part here in L'Hopital's rule. If that condition is not met, L'Hopital's rule cannot be used. That's very important. So that means that still with our limits, we are going to need to check the form, because we have to verify that our form is 0 over 0 before we can proceed with L'Hopital's rule. So let's consider how this works out. Whenever I have a new toy, I like to use it in cases that I could already solve, because it gives me confidence that my answers are good. So let's consider a limit that we already know how to do. We know how to do this limit. We've been doing them since the middle of September. How do I proceed? Check the form. What is that form? And in old school days, we would say, aha, common factor. And so where do we go from here? And what do we get? As x goes to 2, which is, and we're good. Okay, so that's perfectly fine. Now we want to come back and we want to consider how L'Hopital will handle this. So this is our old school method for doing this. And we like it, but it does occur to us that we might end up someday with a polynomial that's really hard to factor, right? Or we might end up with something that's not a polynomial that can't be factored. Let's take a look at how L'Hopital will handle the same thing. Okay, so we begin with this. We check our form. And our form is 0 over 0. This means that our limit meets the condition of L'Hopital's rule. So whereas we have called this form before the indeterminate form, now we're going to be more specific. This form is indeterminate, and it is also L'Hopital's eligible. It is L'Hopital's eligible. What I mean by that is that this is a form for which L'Hopital's rule is valid, and I may proceed using L'Hopital's rule. How does it work? It's really simple. The limit as x goes to 2 of f over g is exactly the same as the limit as x goes to 2 of f prime over g prime, which is 4. Ta-da! Wow, that's cool. That is remarkable because it is so easy to use. Now, when we do our toy problems here, we're not so impressed because we could have done it some other way. Let's pick a hard one and see how it goes. Let's consider the limit as x goes to 0 of sine of 3x minus 2x all over x. Okay? Do we all agree that this is suitably yucky? All right? So, let's consider, is it possible that we could use L'Hopital's rule? Well, we need to first, everybody, check the form. Yeah, exactly. And what does our form turn out to be in this case? 0, which is the magic L'Hopital's eligible form. And therefore, I can say that the limit as x goes to 0 of f over g is the same as the limit as x goes to 0 of f prime. Don't forget the derivative of the inside. And now I can let x go to 0, and I get 3 minus 2 over 1, which is 1, and we're done. Oh, that's beauteous. That's really nice. Let's do some more. About
That's pi.
there we go. Oh, no, actually, minus x works just fine. Yep. Sine, the limit as x goes to 1 of sine pi over 2x minus x all over x minus 1. Go. Okay, what you got, Tony? You're still counting. Okay. Wait, why are you counting? Okay. Tell us what you have so far.
Check the form.
What'd you get?
0 over 0.
Good. So therefore, this is the same as the limit as x goes to 1 of?
Oh,
Ah,
oh, I know what happened. So it's pi over 2 cosine pi over 2x. Pi over 2. And minus 1 for
good. Keep going.
plug y in, which is pi pi over 2 times 0, which is 0. Negative 1 over 1, which is negative 0.
That's it. Good. That's it. Yep. Now, a couple of things about L'Hopital's rule that I need to warn you about. First thing is, don't be that guy. Let me show you what I mean. Every year, I get students that are so enthralled with L'Hopital's rule that they forget to check the form. And so they take perfectly good limits, like this one right here. Okay? If I just check the form, I can see that this limit is equal to 5 over 3, right? No problem. But these students have become so automatic with their use of L'Hopital's rule, forgetting to check the form, that they don't bother to see that the form is not L'Hopital's eligible. And so I have students every year that will try to take something like this and do derivative over top over derivative bottom. No, wrong. Why doesn't this work? Because back when we proved L'Hopital's rule, we required that f and g both be 0 at x equals c. And that did not happen in the case that I just showed you. So don't be that guy that forgets to check the form, because otherwise you're going to use L'Hopital's rule in a circumstance where it does not apply. Okay? Good. That's first thing. Now the second thing is that L'Hopital's rule turns out to be even more powerful than this. Watch what happens. Suppose I consider this limit. Like so. All right. First step, everybody. Yeah, that's right. And my form is L'Hopital's eligible. It's 0 over 0. So I appeal to L'Hopital's rule, and I take the derivative of the top, getting me and the derivative of the bottom, 2x. Huh. But now, as I consider this limit, I consider the form again, and I get 0 over 0. Yes. So I can now iterate. There's our word for the day, right? We call this using recursion. I can iterate through one step at a time until I get to an actual answer. So that I now have the limit as x goes to 0, which gives me 1/2 as my final answer. And I can iterate as many times as I need, so long as my form remains L'Hopital's eligible. How are we doing? Now, the last word of caution that I want to give you about L'Hopital's rule is that L'Hopital's rule does not guarantee that the limit will exist. Let me show you what I mean by that. Let me take the previous problem and change it just a little bit. Okay. As I consider the form for this limit is 0 over 0. And so I think to myself, aha, I can use L'Hopital's rule, which I can. And so I take derivative of top, derivative of bottom. And now, as I consider the form of this limit, this form is actually 1 over 0. What do we call that form? The infinite form. That's exactly right. This limit does not exist. Specifically, as x goes from the left, I get negative infinity. As it goes from the right, I get positive infinity. I'm going to say this limit fails to exist, which means that the original limit also fails to exist as well. the original limit fails to exist as well. Because if it did exist, it would be equal to this thing. Yeah. So L'Hopital's rule, the fact that I get an indeterminate form does not mean that when I resolve that indeterminate form, I will necessarily get a value. It may be the case that my limit does not exist. Does that make sense to everybody? Okay. Questions? Let me give you a clue as to where we're going tomorrow. And I may do one more example along these lines. It is very likely that we're going to have a shortened day tomorrow. Snow and blah, blah, blah. So, just
We have the assembly too, right?
and we have the assembly too. So, yeah. Where we're going to go tomorrow is that we're going to add an indeterminate form to our arsenal that is also L'Hopital's eligible. We're going to have a second form, which is infinity over infinity. And it's going to turn out that we can appeal to L'Hopital's rule in these circumstances as well. So that L'Hopital's rule is going to be an excellent way for us to find horizontal asymptotes. That's where we're headed tomorrow. Let me conclude with one final example here. Sometimes we end up having to evaluate expressions like this. And I call expressions like this derivative-like expressions. The reason that they are derivative-like expressions is that this quantity in the top right here, this entire quantity right here looks very, very similar to the difference quotient. F of x plus h minus f of x all over h. But it's somewhat different from the difference quotient. And so we wonder, what is it in relationship to the difference quotient? We can use L'Hopital's rule to figure that out. If we think of this entire quantity as a function of h with x held constant, and we consider the form, then as h goes to 0, our form will be f of x minus f of x all over 0, so that we have 0 over 0. And I can now appeal to L'Hopital's rule by taking derivatives with respect to h. And when I take the derivative with respect to h in the top, in the first term, I get the derivative of the outside function times the derivative of the inside function. Remember that x is a constant. And I get the derivative of the outside function times the derivative of the inside function. All of that is over 1. And now, as I let h go to 0, I get f prime of x times 2 minus negative 1 times f prime of x so that the result of this entire limit is that I get 3 f primes of x. Now we could have evaluated this derivative-like expression in a slightly different way. What we could have done was to consider some function f and go out 2 h's here and 1 h right there, and taken the difference quotient. The slope of this line is f of x plus 2h minus f of x minus h all over 3h. And since this is the difference quotient, if I let h go to 0, then that is necessarily f prime of x. The limit as h goes to 0 of any difference function will be 0 f prime. When I consider the relationship between this expression and the one that we had originally, you can see that this expression right here is just 3 times my difference quotient. So that I should get 3f prime of x. And so, but that was clever. Whereas L'Hopital's rule lets us calculate it exactly without having to be very clever one. So that's a sneak preview. I'm going to do another example like this tomorrow. Does that make sense? All right. I'll see you tomorrow.